Hi, welcome to the video solution for physics past paper solution. This is Cambridge International Exam, Physics Paper 2, October-November Series 2017. Let's start. Question number 1. One end of a wire is connected to a fixed point. A load is attached to the other end so that the wire hangs vertically. The diameter of D of the wire and the load F are measured as D equal to, these numbers are given, 0.4 plus minus 0.02, F is equal to 25 Newton. For the measurement of the diameter of the wire, state the name of the suitable measuring instrument. A typical question, whenever a question comes regarding measuring of a wire, we always use a micrometer screw gauge. So you can say that we will use micrometer screw gauge. How random errors may be reduced when using the instrument. Again, a typical condition, typical question, whenever measurement of the wire, the instrument is micrometer screw gauge, and how a random error is reduced, or maybe they can ask about how to get accurate reading. So we say that we are going to use micrometer screw gauge and we'll take multiple reading at different places or different orientation, and we are going to use mean value to reduce random error or to get accurate result. Part B. The stress sigma in the wire is calculated by using the expression sigma is equal to 4f pi d square. Show that value of sigma is 1.99 10 to the power 8 Newton meter minus 2. Straightforward question. You just need to plug in the values. F is given, D is also given in a previous part, and these are the values. So you just plug in the values. That means sigma is equal to 4 times of F. F is 25 divided by pi is 3.14 into D square, and D is 0.4. So 0.4, but remember, don't forget this milli. So 0.4 10 to the power minus 3. This is diameter, but we need to put square, diameter square. So when you can use your calculator, you can simplify the equation, and sigma would be equal to 1.99 into 10 to the power 8 Newton meter minus 2. This is the required value. Remember 1.99, or you can round it off till 2. So 2.0 into 10 to the power 8 Newton meter. But as they are requiring the value 1.99, so you leave it at 1.99. Okay, so determine the percentage uncertainty in sigma. So the percentage uncertainty in the sigma is delta sigma, which is the percentage uncertainty. Percentage uncertainty in sigma is delta F by F plus delta D by D into 2 into measured values of sigma. So this is the formula for percentage uncertainty of sigma. So you can say that delta F is the uncertainty in the force, which is 0.5. So 0.5 divided by F. F is 25. So you divide this 0.5 with the 25, and then delta T divided by, so delta D is 0.02 divided by 0.4. So 0.02 divided by 0.4. And remember, because we have a square on the diameter in the formula, this is square. Because of this square, we times this value into calculated values of sigma, which is 1.99 times 1.99 into 10 to the power 8, and if you simplify this you can get answer as 0.12. so delta sigma, percentage of delta sigma is 0.12, or if you multiply by 100 because of the percentage, so 0.12 times, so 0. So in fact delta sigma will be equal to 0.12 multiply by 100 will give you 12%. This is the percentage uncertainty of sigma. Use the information Bi and your answer in B2 to determine the value of sigma with its absolute uncertainty to an appropriate unit. So for absolute uncertainty of sigma is you can say, so absolute uncertainty equal to percentage uncertainty times calculated value. Calculated value. So delta sigma is equal to percentage uncertainty, or the uncertainty 0.12 times 1.99 into 10 to the power 8. And if you do that, delta sigma would be equal to 0.2388 into 10 to the power 8, or more appropriate you round it off 0.22 or 0. Just 2, so 0.2 into 10 to the power 8. So you can write your answer will be 1.99, or you round it off this 1.99 till 2, so you can say that your sigma, your calculated value after rounding off, is 2 into 10 to the power 8 plus or minus 0.2 into 10 to the power 8 Newton meter minus 2. Define the moment of a force. So moment of a force, if you have some object, a rod maybe, fixed at some point like this, and you apply some force away from this point, and this point is called pivot, and this is force F. So from the point of application or point of action on the force till pivot point, this distance, this is the distance, and this distance is denoted by d, which is called perpendicular distance to the force. So F times d gives you moment, and this is the definition, mathematical form of moment, or you can say the turning effect of a force is called, due to F object turns, that's why turning effect of a force is called moment. So that's how you can define moment. A thin disk of a radius r is supported at its center O by a pin. The disk is supported so that it is vertical. Three forces act in the plane of a disk as shown in figure 2.1. So this is 1.2 acting right, 1.2 acting left. Okay, 6 Newton making angle theta. Okay, two horizontal and opposite forces each of magnitude 1.2 Newton act at points A and B on the edge of the disk. A force of 6 Newton at an angle theta below the horizontal acts on the midpoint C of the radial line of the disk, as shown in the figure 2.1. The disk has negligible weight and is in equilibrium. State an expression in terms of R for the torque of the couple due to the forces at A and B acting on the disk. Okay, so see, they are talking about torque due to couple. Remember, whenever we have two equal forces acting in opposite direction, equal in terms of magnitude. So we have a force F1 and we have a force F2, and both forces are acting in opposite direction, but magnitude of both forces are equal. And clearly this object is going to rotate or turn in that direction. So we have a moment of, in this case we say we have a torque due to these two forces. These two forces are called couple. So this rod is going to turn about the center, and if you need to find the torque, so torque would be equal to magnitude of any one of the force, because magnitudes are same. So you can take magnitude of one force F times distance between the forces. Distance between the forces. So from F1 to F2, this is distance. We take F into D. This is called torque of the couple. If you see the diagram, you have 1.2 Newton acting right, 1.2 Newton acting left, and the distance between these two forces is diameter of the disk. So you can say that torque would be equal to magnitude of one force 1.2 times distance between the forces, which is 2r, and then 2.4 r, and this will be your clockwise moment. Clockwise. Friction between the disk and the pin is negligible. Determine the angle theta. Okay, if we need to find the theta, we need to see the diagram. This is the diagram. We know that we have a clockwise moment due to a couple of forces, or torque due to a couple of forces, and this is a clockwise moment. And if you see the 6 Newton force, due to 6 Newton, we have anti-clockwise moment. But 6 Newton is making angle theta. So whenever we have theta angle, or we don't have a perpendicular distance, we resolve force into its component. So this is the head of the force and this is the tail. So we can resolve force into these two components. Clearly, this is horizontal component of 6 Newton. This is vertical component of 6 Newton. Horizontal component is passing through point O, pivot. So horizontal component is not going to produce any torque or any moment, but this vertical component is going to produce this anti-clockwise moment, and this vertical component is 6 sine theta. So you can say that because disk is in equilibrium, so anti-clockwise moment must be equal to clockwise moment, because disk is in equilibrium. So anti-clockwise moment is force into perpendicular distance. So force is 6 sine theta, perpendicular distance is r by 2. If you see, this is the distance between pivot and the point of action of the force. So this distance is perpendicular distance for 6 sine theta is equal to clockwise moment, and clockwise moment we found in the previous part, 2.4 r. So r gets cancelled. This is 2.4, and sine theta is equal to 2.4 divided by 3. So theta is equal to 53.1 degree or 53 degree. State the magnitude of the force of the pin on the disc. Clearly on the disc we have a 6 Newton force acting in that direction. Disc is in equilibrium. That means all forces must be balanced. So left forces must be equal to the right forces, upward forces equal to downward forces. So according to Newton's third law, if we have a 6 Newton force acting in that direction, that means this the pin is applying 6 Newton force in that direction in order to balance, or in order to remains in equilibrium. So force of the pin on the disc is 6.0 Newton. Question number 3, a spring is attached at one end to a fixed point and hangs vertically with a cube attached to the other end. The cube is initially held so that the spring has a zero extension as shown in the figure 3.1. So this is figure 3.1. Okay, so this is zero extension, original shape, weight 4 Newton, 1000 is density. Okay, the cube has weight 4 Newton and the side is 5.1 centimeter. The cube is released and sinks into water as the spring extends. Case number 2. The cube reaches equilibrium with its base at the depth of 7 centimeter below the water surface as shown in figure 3.2. The density of water is 1000 kg per meter cube. Calculate the difference in the pressure exerted by the water on the bottom face and on the top face of the cube. So pressure exerted by water. If you recall, if something or some object immersed in a fluid, if this is, it's a fluid, and we have object, we have some object immersed, and this is the depth from here till here. This is the depth d. So the pressure on this object at the top surface, or whatever the distance is, pressure is equal to rho g h. And if we need to find the difference of pressure between the bottom and the top, that means we need to take the difference, we need only the difference between the height, which is 5.1, and the 7. So you can say that pressure would be equal to rho g and change in the depth or distance between the faces. So you can say that rho is 1000 times g, 9.81, and the height difference or the depth difference between the two faces is 7 minus 5.1, and clearly this is centimeter and 5.1 also centimeter, so you must multiply 10 to the power minus 2. And if you calculate this, the pressure will be equal to 500 Pascal. So this is the pressure exerted by the water. This is the difference of the pressure exerted by the motor. Use your answer in A to show that the upthrust on the cube is 1.3 Newton. So we need to use the answer in A, and in A we found the pressure exerted by the water. So pressure is basically force per unit area, and in this equation this force is in fact the upthrust. So if you find the F, that means you can find the upthrust. So upthrust is equal to, or F is equal to, or upthrust is equal to F, which is equal to pressure into area. So you can say that pressure is 500 times area, and area is area of the cube. So 5.1 into 10 to the power minus 2, because it was centimeter. So length, this is length into height, so square area. And if you simplify this, so upthrust would be equal to 1.3 Newton. Calculate the force exerted on the spring by the cube when it is in equilibrium in the water. If you have a cube, so cube has its weight acting down, upthrust acting upward, and this cube is connected by some one spring. So this weight is pulling this spring down. So you have a tension in the spring. So this tension is trying to pull the object up. So tension is in upward direction. So you can say that because the object is in equilibrium, so T plus upthrust must be equal to W. That means T is equal to W minus U. So 4 minus 1.3. So T is equal to, or force F, whatever you say, tension or force, this is equal to 2.7 Newton. The spring obeys Hooke's law and has a spring constant 30 Newton meter. Determine the initial height above the water surface of the base of the cube before it was released. So now you can see that you had a surface of a water, something like this. An object was here before releasing at that moment, and it was the spring at zero extension. So this is the height above the extension that we need to find in this question. Determine the initial height above the water. We need to find this height. And when it is released, spring is stretched and it is 7 centimeter, like this. So we can find the total extension like this using the given condition. So we know that according to Hooke's law, F is equal to Kx. And X, remember, X is the extension due to this force, and the force acting on the spring is 2.7 Newton. This is the resultant force. You can say that this is the resultant force. So F is 2.7 is equal to K is 30 times X, and if you if you simplify this equation, so X is equal to 9 centimeter, and clearly this X is from initial to the final position. So this above the required height, I'm calling it delta X, is equal to 9 minus 7. So delta X is equal to 2 centimeter. The cube in the water is released from the spring. Determine the initial acceleration of the cube. When the cube is released, we know that we have a resultant force F acting on the system, which is when it is released, we have a force 2.7 Newton. At that moment. So initially we have a force 2.7 Newton, and due to this force the object is going to accelerate initially. So F is equal to ma. So F is 2.7 and mass is not given, but weight of the hanging object is giving, which is 4 Newton. So 4 divided by 9.81 is the mass into acceleration. And if you simplify for A, so acceleration would be equal to 6.62 meter second minus 2. This is initial acceleration. Describe and explain the variation, if any, of the acceleration of the cube as it sinks in the water. Now, before releasing, object was at equilibrium, so all forces were balanced. But as it starts sinking, it experiencing a net downward force, which was, we say that it is 2.7 Newton, and then it is accelerating down. But as it starts moving, remember, when any substance or any object especially moves through a fluid, it experiences a drag force, which is called viscous drag. So as it keeps moving or accelerating, viscous drag starts acting on this object and keep increasing with the speed. And the time comes when viscous drag plus upthrust balance the weight. So situation is, initially you can see that initially this is the object experiencing upthrust and the weight. When it is released from the spring, we know that we have a downward force, which is 2.7 Newton. This is resultant force. But as it starts moving down, like from here to here, along with weight and the upthrust, a drag force starts acting in upward direction, D. And this drag force keeps increasing because its speed is increasing. But there is a time when drag and upthrust sum equals the weight. So you can see that D plus U equal the weight. At that moment, acceleration becomes 0. So you can say that as drag starts acting, so acceleration starts decreasing until it becomes 0 at this condition. You can add this statement at that point, acceleration equals 0. Question number 4, state the condition required for the formation of stationary waves. So stationary waves, when two waves moves in opposite direction, one is coming from left and the other one is coming from right. When two waves moving in opposite direction, and if these waves are coherent, that means same types of waves, same amplitude and period, then after superposing or overlapping, they gives us pattern of nodes and antinodes or stationary waves. So conditions are two coherent waves moving in opposite direction. B. A horizontal string is stretched between two fixed points x and y. The string is made to vibrate vertically so that the stationary wave is formed. At one instant, each particle of the string is at its maximum displacement as shown in the figure. So this is a string, okay, point P, fine. The total length is 2 meters. P and Q are two particles of the strings. The string vibrates with a frequency of 40 Hz. Distance x and y is 2 meters. State the number of antinodes and the stationary waves. So number of antinode. Antinode is point of maximum. So this is first antinode, second, third, fourth, and fifth. So number of antinodes are 5. Determine the minimum time taken for the particle P to travel from its lowest point to its highest point. That means we need to find the time to reach the point P from the bottom to the maximum height. And if you see this should be half of the time period. So first we figure out the time period. So the time period T is 1 upon f, as frequency is given. If you do 1 upon 40, it will give you 0.025. Second, this is the time period, and we need to find half of its time period. So T is equal to, this is half of the time period, capital T by 2. That means if you divide it 2, so you can write the time period as 1.25 into 10 to the power minus 2 second. State the phase difference with its a unit between the vibration of particle P and of particle Q. So we need to see the diagram. This is the diagram. Clearly you need to find the phase difference between the particle P and Q. So this is not traveling waves, this is stationary waves, and stationary waves we have oscillation up and down in this case. So particle Q will be coming down and particle P will be moving up. So exactly opposite in motion. So we have a 180 degree phase difference, or you can say pi radian, the phase difference. Determine the speed of a progressive wave along the string. If we need to find the speed of the wave, so idea is speed of a wave V is frequency times wavelength. We have frequency which is 40, but we don't have lambda or the wavelength, and we need to figure out lambda first. And it is stationary waves, so we know that we can count the number of loops and the length is given. We can relate this length with the number of loops and we can figure out the wavelength. So we know that we have 1, 2, 3, 4 and 5 loops. That means 5 by 2 lambda is equal to the length of the string, which is 2.0 meter. And if you simplify this, then lambda is equal to 4 by 5. 4 by 5 meter. This is the wavelength. Now velocity you can find V is equal to frequency. Frequency is 40 times wavelength, which is 4 by 5, and 5 and this cancel. So V is equal to 32 meter second inverse. This is the speed of the wave producing in this string. Thank you very much for this video. I hope you enjoyed it. See you in the next one. Have a nice time. Bye.